This is going to be our last session of the day and of the week. It is my great pleasure to introduce Yinyu, professor at Stanford. Where to begin on introducing you? So Yinyu has done really foundational work across all of optimization theory, written a book on nonlinear and linear optimization, been one of the pioneers of interior point methods, more awards that I can count. I was looking at something on your website about like 55,000 citations for papers or something like this. And it's really my pleasure to introduce Yinyu for this talk at the end. All week we've talked at various points about certain algorithmic breakthroughs and advances that in some way, shape, or form used interior point methods or related to something about interior point methods, but we haven't really gone into depth on interior point methods, and that is the last thing we will be doing for this bootcamp week. Yinyu is one of the pioneers of this subject, and I am delighted to hear your talk on the subject. Thank you.
Good. Thank you for Aaron, my colleague, and introduction. I'm going to, good to see all the young people and also old friends. So Aaron asked me to give a very, very elementary, like a basic concept introduction of the so-called interior point algorithms. So what I'm going to do is the first part, I'm going to focus on some basic, concept in interior point algorithms, maybe some perspective how to looking at the interior point algorithms. Then second part is going to be a little bit more advanced on the coverage of the central path. So the overall objective still want to focus on linear programming and whether we can really get the so-called strongly polynomial time algorithms. Okay, for me, that's the central question and the fundamental. Just that linear programming still remain a very, very open field for everybody jumping and try to lock that question down. Right? Okay, so I'm going to go slowly, and this is a boot camp. Okay, this is I borrowed this slide from the Daniel Daducci and also Bento. Bento is supposed to be also here, and this slide is basically what's the linear programming is about. Okay, so linear programming is still try to finding a polyhedral and the constraints, polytope, 2D, and you try to find the optimal solution. Has been the focus of the whole optimization, how to develop efficient algorithms. Then we have a simplex method. We have recently have some circuit walk algorithms, and of course the central path. And then interior point algorithm follow this central path. There was some other just like ad hoc and like a black box algorithms. So what I'm going to do is I'm going to focus on this IPN, interior point algorithms. Okay, so I thought here's the linear programming. I'm going to in this basic form. I'm choosing X, which is the vector, and minimize the linear objective functions subject to constraints. I'm writing in this abstract Ax equal to B form. X has to be non-negative, component-wise when I say X. Okay. So that's our problems. Okay. A basic concept interior point algorithm is defined what's the interior of this feasible region. Okay, so the feasible region is defined by the so-called interior is by component-wise, each one is strictly positive. Okay, so interior point algorithm will start with the feasible region, have such a strictly positive feasible solution, satisfy those equations. Okay, same thing for the dual problems. So everybody understand what's the dual. Dual is have this slack variables, have this y variables, we have to be greater equal to 0. We assume this is not, also not empty either. Okay, so With these conditions, well, we know, of course, even any feasible LP, we use Z star to denote the optimal value. We basically want to find a solution such that the duality gap is less than epsilon. Okay, so for simplicity, we assume we have an interior point pair, which is start with. So we have a solution x0 strictly positive, satisfy equations. We also have a y0 satisfy snack variable, also strictly positive. Okay. So interior product are attributed to Kamakar. Okay, of course, Reiniger, and just who has done fundamental work on this area. Okay, so a key associated with this linear programming is defined as the so-called logarithmic barrier functions. Okay, so in that primal feasible region, we want to finding a sum of log xg, which is the maximized. But usually we take log. You know? Yeah, so we minimize, we put negative. Same thing, we put the dual, we add a log functions. Okay, so this is called the logarithmic barrier. So this problem itself assumes this feasible region is bounded, has an interior. The dual also bounded, has an interior. Then the minimizer or the maximizer for this always exists. Okay, so this is a so-called linearly constrained convex programs. This problem actually started much early because this is so-called barrier functions. If you want to prevent x goes to 0, you want to maximize them. Okay, so this is what now. Okay, the maximizer for this problem, because this is a strong convex problem for doing strong concave functions. So the minimizer is unique. Okay, so this unique minimizer, what we give a name, is called the Analytical Center. Okay, there was many different ways define a center in a polytope, correct? Okay, so if you give any polytope, if you have some polytope which is defined, okay, let's say, does this pen work? Okay, so yeah, you can define analytical center, give them, for example, center of gravity, that's a center. Okay, you can define like a lot of like a center, minimize mean of the distance to each polytope, and that's also a center. Somehow, the center gravity is very hard to compute. Even volume is hard. So some other center, for example, minimize small distance. Sometimes center is not unique, but some other notion. But this logarithmic barrier center is also very nice. Okay, so you can also think about these two problems actually also a primal and dual problems. So logarithmic barrier function have this self-dual property. Okay, you find a Lagrangian dual. For example, you find what's the dual of this problem, it becomes this problem. So it's because they're unique, we call it analytical center. And this can be written, for example, the analytical center for these primal problems. You can write of this into these optimal conditions. Okay, you can write this x equal to E, and this is E is the vector of all ones. Okay, so it's just a satisfied primal feasible region. This is a dual. Of course, the dual become a homogeneous, and you can do so. Give the name to this problem. This goes back to 88, Sullivan and Bayer Nagaris, and also Megiddo also, analyze the property of this analytical center. Okay. So this also goes to the dual feasible region. You see this center all gives the same condition. If you go to the dual feasible solution, and basically the dual is maximize this one, right? What's this? This is all snack variables, right? What's the snack variable represented in the dual polytope? Is the distance to each of these constraints. Okay, so you maximize the sum of log. That's the same as maximize the product. Okay, so you can see once you maximize product, each of these snack variables value, you don't want this to be on the boundary. Okay, so that's the analytical center. That's the geometric center. Okay. There was also other centers. You can maximize some deterministic, like goes to Vaja, and built on that one, Aaron and many other people also did a wonderful work. Okay, but somehow this analytical volume still, for this simplicity, still played a very, very important role. Okay, so this one is dependent. So why we call the analytical center? That's because this center is not invariant with the representation of the polytope. For example, you just consider this feasible region. It's an interval, one-dimensional. Y greater equal to 0, another y greater less equal to 1. That's to represent the interval in one dimension is 0 to 1. The analytic, if you just represent this one, analytical center is just a half, right in the middle of interval. But however, if you repeat this constraint like n times, what happened? You still same intervals, but your center shift. Okay, so that's why we call this as analytical center. It's really function of A and C. It's not invariant in terms of the geometry. So it really depends on representation. You may think this is the bad thing, but this can be also a good thing because it's the analytical. You can do a lot of things, analyze what's the very smooth, very continuous and stuff. Okay, so later on, I'm going to show you something. Okay, so that's why we call this as analytical. Really, you represent this same kind of geometry object, but different A and C, and the analytical center shift. Okay, so that's why somehow linear programming is also very hard, especially when you want to establish a lower bound. Then basically people add some crazy inequality constraint to make it very hard to solve, because any linear program you solve, they can only recognize A and C. They cannot see what's going on in the real shape of the feasible region. So, okay. So with this analytical center, we also defined what's the volume. I know typical volume in the common sense, you have a volume. What's the size of the polytope feasible region, right? For example, the intervals, just length is equal to 1. However, because the representation differently, you can also define what's the analytical volume. Okay, what is the analytical volume? It's basically for any point, you just product those maximizer, the product of those snack values, you can define as analytical volume. So analytical center, that also, because you maximize and the product of those things, you can use that matches the size of the polytope. Okay, so that's the whole idea, which people call, this is called the potential functions. It's called the analytical volumes. Okay, so what's the property? To me, most algorithms, if you want to get some kind of a polynomial improvement, like an ellipsoid, what do? You cut something, ellipsoid volumes reduced. So the set contain optimal solution is always shrinking. That's how you develop some kind of convergence things. Okay, so you can do all the things, but does interior point also have this kind of a geometrical interpretation? It's really reduce some kind of a volume. It turns out it is. It is reduced analytical volume of a polytope contains the optimal solution. Okay, so in some sense, for example, what's the property? And let me just give you this picture. Suppose we have 1, 2, 3, 4, 5 inequalities, okay? Represented by some linear inequality. We have defined a center, okay? Now suppose one of the hyperplane replaced, cut through the current analytical center. How much analytical volume of this new smaller polytope compared to the old one? Okay, that makes sense? You can think about this as one of your objective hyperplanes, right? It was originally placed over here. Now I really want to minimize this. Then I placed over here. I compute the new analytical center. Then I move this again, cut this, a sequential cut through this analytical center, right? Not like an ellipsoid method or something, whatever. Now the question is, we know the polytope is getting smaller and smaller. But the two successive volumes decreased by how much? So, okay. So this is the geometric interpretation, okay? So basically, very easy. I replaced, let's say, we have this, we define this. Let's say C1 is replaced. C1 moved to C1 plus. C1 plus actually equal to this. The rest of them is unchanged. It's defined, is shrink more than half. It's e to the negative 1. Okay? The proof is very simple, very elementary. Just write down the optimal condition for the two successive representation of the polytope. They use these analytical properties. Okay? Actually, if you want to take a look, it's just per page. Yeah, just use this n-1 times 1. This is n is the number for those inequalities. Very elementary. Okay. So this immediately gives you arguments, like an analytical center cutting plane method. You keep translating your objective hyperplane, and downward to go to optimality. Of course, the issues sometimes this actually eventually is the Renniger's arguments. So when you move this objective hyperplane downward, you don't move until you cut through center. You give some room, the current center still in the interior of the new feasible region. I'm only cut halfway, okay? Because the e to the -1, I don't need to be that aggressive. Then you can compute the new analytical center from the old center, because the old center still in the interior of the new polytope. 1 Newton step, you will do it. Okay. So that's the different geometric interpretation, rather than just in terms of the objective value, how much getting closer. It's just analyze this analytical volume. Because why? Because this volume maybe also give you a new perspective. Now, suppose, okay, so here's the proof. Suppose now I go back to these pictures. This is something in the ellipsoid method very hard to do. How about I translate two hyperplane? I will understand what I mean, okay? Not only this objective need the hyperplane transferred, I also need to value this one. So you have one cut through over there and another one cut over here, okay? Now I give the picture, which looks like this. So this one also needs to translate it over there. So it's like this. This new polytope, after two hyperplane translated, even becomes smaller, right? I'm asked the same question. How much volume decreased from the old one by translating 2 cuts. The ellipsoid method is very hard to do. Actually, people want to do ellipsoid, okay? And it's very hard to find the smallest volume contain half ellipsoid. It's very hard to contain a sector, because once you contain the 2 hyperplane become very hard. Okay. What's the answer? Answer is conventional to negative K. Okay? It's the number of hyperplane you translated. Of course, if you have too many hyperplane translated, then your new center can be hard to compute. So you don't want to translate too much. So this property, actually, so the one application of this property is, well, if I only have one objective, I need to translate this. Only translate one ellipsoid in one cut, only give me reduction e to the -1, right? How should I take advantage of this property? It's proportional to the number of cuts you translated. What do? If this is your objective hyperplane, you copy them k times. Remember? I still represent objective have more weight instead. So this is my objective hyperplane, something less than something. I repeat them same hyperplane k times. Polytope does not change, but because I duplicate times, I translated one of them and translated k of them, I get more reduction. That's the idea. And if we go back, of course, Jim Redigan may not from this. The objective hyperplane is weighted square root n times. That's how you get a reduction, square root n improvement. Why square root n? Why not n times? Once you translate too much, the new center can be hard to compute, okay? So you push them too far. So this is a weight interpretation and how to this. Any question? Yes.
So when you duplicate the objective
yes.
times, doesn't the analytical volume also go up because of that duplication?
Yes. So you have to analytical value, but go back to just logarithmic, just 2n, whatever kind of things. Yeah. So if you only duplicate the square root n, it's n plus square root n, but you reduce the very dramatically. That's right. There was a balance over there.
Maybe one more question.
Yeah.
You were to tell us how this you're going to view interior point of path following as this translation later on.
Yes. Yeah, this is eventually it is a translation. Actually. Yes. Yeah. Actually, yeah. Okay. Yeah. This is the path following algorithm. This is just if you think about it, you continue to translate those hyperplanes. The analytical center will form a path. That's the so-called central path. That's the geometric interpretation of the central path. Of course, you can parameterize it by different parameters in terms of the duality gap.
So why is this the first time many of us are hearing this?
So we don't quite see why this is the central path. Could you?
Oh, okay. So suppose you only translate this infinite small amount. The analytical center will shift, correct? You continue to push these hyperplanes gradually. This analytical center also gradually moves, right?
But why is this the same as the central path?
Oh, yes. So later on, you can formulate by anything. You can write what's the algebraic curve of this path. Then you prove that central path is the same as the mu parameterized by mu, whatever. Yeah, basically you forming this kind of invariant, like a 1-1 correspondence, whatever. Yeah. So this is what you can. All I'm trying to say is it's very easy. That's the advantage of the analytical things. You can do very deep. Okay, so you can do multiple cuts. Okay, so now you have an analytical center cutting plane method, and you can really reduce this. Well, of course, we did not translate. This kind of things is going to become instead like a differential equation with discrete equations. And then you translate by something, it's become a piecewise linear and follow that path, whatever. I'm going to, you can prove this is exactly the central path following. So what's the application? Suppose you have a multiple objective. I really want finding a Pareto optimal solution for multiple objectives. What do you do? So this one way to do this, you can weight different objectives, right? Let them all move, in some fashion. For example, I really want, suppose I have, suppose my feasible region like this. I really want to maximize the objective on this direction. I also want to maximize the objective on that direction. So from here, I move it. From here, I move it. If you just waited, many people dealing with multiple objective. By the way, there was many in economics. You really have multiple objective. Really want Pareto. So if you do something like this, you just weighted these things, maybe the solution will become these solutions. Because any different weight will move you to the one of the corner solution. But if you think about this, you can use this analytical card. First, I move this object a little bit, have an analytical center, then move this a little bit, I just alternately move it. It will give you a solution what? It's always in the middle of this line. So many people think about this solution, although in terms of, if you just simply average it into one weighted sentence, the solution may give you some corner solutions. Okay, even you weighted by exact half, maybe still give you a corner solution because the whole phase becomes the optimal solution that weighted sum objective. So it could be here, could be here, could be here. But in terms of these two objectives, people usually think, what's the fair solution? Where's the fair Pareto? Not only want a Pareto optimal. Pareto optimal, so you can improve one without suffering other, right? But any corner solution over here is the Pareto. But which one is the fair? You can use this alternating cutting per objective or simultaneous move them, then that will give you a solution in the middle. And also you converge it very fast because new analytical center. Yeah, but of course, you say linear programming, I only have a single objective. What I do, I just duplicate it. Yes?
Is there a way to use this to identify that entire facet is the set of Pareto optimal solutions?
Oh, that's a good question. Yeah, I think it depends on your sequence of how to move each objective. Maybe if you can, I don't know, maybe they always give you one converge to one solution if you fix the order of those translations. If you always fix them, they only converge to one point. But different orders, different things, maybe give you need to point.
So
Okay.
there's no one canonical ordering.
Yeah, there was no, I don't think this can be identified the entire optimal solution facet.
Yeah.
And yeah, that's a good question. But probably we still need to, but maybe we can identify the optimal facet for linear programming. So later on, I'm going to talk about maybe that are related. So we cannot finding all the possible corner solutions, all the but we can find what's the definition of the optimal facet. Yeah, I don't know exact answer to that question. That's yeah. But anyway, so this is you can alternatively or follow different orders or simultaneous with the fixed proportions or something, because you cut through always cut same moving the same speed. They will convert to one solution according to what the speed, what's the proportion of speed you cut. But anyway, this is actually what when you compute one like a facial market, which is the weighted analytical center. What you do is just you can apply this method, come to one of those equilibrium point. Now the central path. Okay, so this is what I scaled. You duplicate the k times. You can follow this, but it's really that yeah. So this is gives you analytical center. Just push. You can think about this, the push, and then you can define this analytical center. And but however, as I said, very good. A better regularization is use barrier functions. But exactly the same way. Okay, so I prove that successive center cutting plane by infinitesimal movement, which move the analytical center. But that's the same thing as by linear programming, you add a barrier function, which I talked about before, but the parameterized by mu. Same thing to the dual. You add those, this should be S, this is in the dual feasible region, same thing in the primal feasible region, do this. Okay. It turned out, due of this problem, if you write, there was all different Lagrangian dual, bench, whatever, French dual or something. It can write the dual of this problem is this, the dual of this problem is this. So log function have this self-duality property. So some of the, for some order optimizers ones, they know barrier function is not unique. Barrier function is any function, if you approach the boundary, that goes to infinity, right? For example, 1 over s is also a barrier function. But 1 over s, that barrier function is not self-dual. Actually, if you read that problem, you would have read that does not give you a barrier function for this problem. So that maybe when you're teaching student ask why you have to use logarithmic do a barrier function. One answer is it have very good self-duality property. Originally linear program primal dual, after barrier, it's still primal dual. Yes.
What would be the dual of 1 over s?
Huh?
What would be the dual of 1 over s, J?
Oh, actually, I don't remember. It's become a square root of something. It's something. It's like a polynomial or some polynomial. Yeah, you can write very explicitly. It does not have a good dual property. Yes.
Where will this duality show up? Like, will we be able to see this? Why this duality is important?
Oh, yes. So whenever you have a convex, or this become a nonlinear optimization problem, right? With some linear constraints. What you do is you always form the Lagrangian functions. Then you write that optimal condition with Lagrangian functions. Then you can construct the dual problem. Yeah. So because this is log, it becomes a dual. It becomes log again. Whatever.
Why is this? Why is it important that both are log? Like why will it be useful?
Oh, so first it has a log. Have these duality functions. Is the self-dual. So I minimize one of them. It's actually the same minimize the other one with this parameterization with the dual. Okay, so it is like now you can use a primal dual, and then later on you can find the log S also have very good and alpha concordant barrier function have some property. Newton method especially good. Those kind of things. Yeah. So when you're working on some optimization problem, if that optimization is self-dual, they usually give some advantages to control it. Okay, so it's like you automatically work for one of them, you work for another. They all aimed at the same kind of each help each other. Without self-dual, sometimes it's very hard. Okay. Yes.
Is there any example, other example that you get a self-dual barrier?
For barrier function, this is the only one.
The only
For non-active orphan. Of course, you may have a different, for example, semi-definite programming. The barrier function log determinant of matrix. That you what can I do? They also it's like the same thing. It's like a dual, and those kind of things. Yeah. So yeah, this you have more barrier function, but depending on different cone. For these non-active cones, this log function, according to my knowledge, only S log S is self-dual. Okay. So you may add any polynomial, you can write down explicitly what it looks like. So this so for example, one advantage is because they are self-dual, you write optimal condition for this one, that optimal condition is the same for this one. Okay, so that's the one of the optimal self-dual property whatever. Okay, so you have one characterization characterized with the central parts, all parameterized by this mu. So what is this xs? So this is basically a point where this is basically xj times sj equal to mu for all the j. So I usually students in my class they like matrix representation. So this big X is like a diagonal of those X vector. So this times this just a component-wise product. They all equal to the same mu. It turns out once you satisfy these conditions, X for any given mu, X is the minimizer for this, Y is the maximizer for this. You see, because they're self-dual. So you solve one of them, you get the other one as the byproduct. So because again, it's the uniqueness, so you can think about this solution. You can write down these ones. So this is what you can do it. As long as they are satisfied this, you can prove the uniqueness and everything. Then you can parameterize it by mu as for any given mu. So you take a derivative with respect to mu and everything. You can do all the crazy things. But anyway, x mu, y mu, s mu constitute a path, one-dimensional path. One is the primal feasible region, another one is the dual feasible region. They come one to one. Okay, always have a pair associated with same mu, not parameter. You can prove that's the same as your translator. They are analytical center associated with some objective card. So this is so-called, yeah, you can also do this. I don't know. There was many properties. Okay, so this is also I really want to emphasize. Of course, if as mu goes to 0 and this path of this maximize or minimize converge to a solution, okay, optimal solution. But sometimes, if your optimal solution set, if your optimal solution is unique, what is it converges to? The path still converges because it's the algebraic curve. They ended at a single point. The paths always converge to, in this case, suppose your linear program or objective hyperplane exactly parallel to this. Okay? This path converges to a point in the optimal solution set. That point is analytical center with all this one to be tight, but it's still including all other inequality as a constraint with a defined analytical center of that optimal solution phase. Some become 0, okay? Some slack variable becomes 0. You fix them equal to 0. You still consider all other inequalities. You always converge to an interior point. But not only the interior point, it still remains analytical center in that facet. So you, from a higher dimensional facet, analytical converge to a lower dimensional facet, the center. So they will converge to this point. Actually, we'll be able to identify those facets. Okay, so I just say this property become very important, especially in the presence of some kind of which point. If this entire line segment is optimal solution, so in terms of the economic revenue or some profit, doesn't matter which point. Okay, you use, you give the same linear objective. Again, people ask, if optimal solution in terms of this priority objective is multiple, then which point would be better? Can you still rank those solutions one way or another? You know, in terms of objective function, doesn't make a difference. Okay. This the recent work is on again coming on the fairness, which is the fair optimal solution. Okay, many people think the fair solution should be some kind of an average of all the optimal solutions, correct? And analytical center is one of those. Not only that, so this has become an issue. In the old days, we think interior point map solution does not give you a corner solution. It may be a bad thing. Now you can think about maybe this is a good thing because they give you a fair solution. It's the average of all the optimal solutions. Okay, because if this would be resource allocation, corner solution may be biased against the other group. Another advantage is in many, especially in online linear programming. What is the online linear programming? Here we decide what's the value for x1 to xn all together, wait until information. But in some situation, the solution together with the associated information come sequentially. You have to decide one immediately those point information arrives. You cannot wait until completely A, B, C are constructed. This is the typical many machine learning problem has this kind of so-called online learning or online linear programming. One of the assumptions most of the algorithm, they basically you want to learn the shadow price. But if a shadow price is not unique, what do you use? To me, when you develop learning and generalization bound, those kind of things, you always assume the things you want to learn, the target is unique. But then the target itself is fuzzy. Many points can represent. How do you develop the algorithm to learn fast? Then you can use that analytical center because it's still unique, still optimal. So you have a fixed target, okay, unmovable target to learn it. So this is some applications, okay. So yeah, the proof actually is not, it's also very elementary. So this part is the regular, and so is the math, he's the mathematician, okay. So anyway, you can this path following parameterized by this mu. So each time we can discrete reduce mu. You know, you solve that. This is called the primal dual. Yeah, the algorithms. Okay. Anyway, so you can reduce mu by this square root n. This is equivalent to duplicate our objective by square root n times. And at the same time, you can compute a new center in 1 Newton step. So that's the trade-off. So this is all. The reason of course, Jim Renegan's algorithm originally is the dual-based. They only updated the dual, but somehow because the self-duality, you only working on the dual is equivalent is still working on the primal. There was the most popular one. I know probably most people here don't care what's the practical computation efficiency, but in practice, people use the primal dual Newton method. So basically update the primal and the dual simultaneously. So they basically get that single optimal condition is some kind of nonlinear equations. You just apply Newton to it. Working on both primal dual level. Okay. So that's the way, that's the most, okay. Yes?
So could you one more time say why this square root n appears?
Yeah, so square root n appears is because, so the algorithm is basically, they define some neighborhood. Nobody is going to compute the exact analytical center for that given mu, okay? So, for example, what's the given mu? What is the exact analytical center? Analytical center is xik, xj, sik equal to mu k, right? But however, we always allow them to in some kind of a neighborhood. So the neighborhood, you can use different norm defined by eta, which is the 0, 1 number times mu k. Okay. So we don't need to compute the exact analytical center, basically. Exactly central path point. We allow some errors. Then we reduce this mu k by some gamma. Gamma is also between 0 and 1. We want a mu, that parameter goes to 0, right? We said that goes to optimal solution set. So gamma control how aggressively you reduce mu, okay, to the new, okay. You can think about this as new is the next mu, whatever. This is the previous mu. So then you want this new, you want xs equal to this new mu. What do? You just apply Newton method. Still in the feasible region space, still in the dual, those are linear. The only nonlinear things is here. But this is more symmetric Newton. So what you can prove, we know this is the numeric class 1. How should I reduce lambda such that this new iterate k plus 1, k plus 1, k plus 1 still in the same neighborhood, but here replaced by k plus 1. So this is people called homotopy type of things. You keep reduce mu, you always trace that mu, not exactly, but in some neighborhood. So it turns out how aggressive you can reduce lambda. it turns out this number comes out. So this is exactly what I talk about. It's actually 1. So this would be 1 minus the square root and this number. It's all from the proof. Can you go beyond that? Okay, people usually say, oh, maybe we should come. But if you restrict it only 1 Newton step, this is how much you can do it. So that's what you give. Each time you reduce mu by this factor, which is this number. So this number, after square root n step, you reduce the mu by half, by constant. Yeah. So that's what the square root n comes in. But that's the same thing. It's the balance between how much you want to duplicate, how much you can compute a new something in 1 step, because you have to trade. The best turn out to be square root n. So that's this number comes. Well, unfortunately, if you give this algorithm, always reduce gamma by this one. So this is a fixed geometric convergence rate. You prove the square root n, you need the square root n step. Your algorithm will perform square root n step in order to reduce mu by a half. But people say that's not adaptive enough. It's not practical. If I implement this algorithm according to this fashion, always reduce, it's like without, now, people say it's like a parameter, like a step size. If you fix that step size, nobody can get efficient practical algorithms. Okay. So what people do is convey more adaptive, not the algorithm itself to choose the step size. Okay, so one idea to choose this step size is so-called adaptive pathology. So this has to be implemented, the theoretical work in the Mizono-Tart. What I'm just saying basic idea. We define 2 neighborhoods. So one neighborhood is what that neighborhood, okay? Then we define another neighborhood slightly large. At any given point, we go a point, shoot in a large neighborhood. Then we apply another Newton step, always come back in the smaller neighborhood. The length, how much you reduce mu, is completely decided by how smooth the central path it is. If the path is almost like a single line, with this approach, you shoot to optimal solution very fast. So every step contains 2 steps. I'm just giving you, sometimes how to turn a theoretical algorithm into a practically efficient. Otherwise, we just cannot compete with those AI people. They always tune the parameter, doing something. Then they automatically make the algorithm adaptive, whatever kind of thing. So anyway, that's the reality right now. We have to compete with those guys. So anyway, so this is one way to make this algorithm. This eventually is everybody implemented in practice. It's even more sophisticated. Yeah.
The equation is just the right-hand side.
Oh, yes, that's a great question. So we define this neighborhood by eta, right? So you define one eta is 0.9, another smaller than is 0.5, let's say. Okay, that from 0.5, 0.9 make a huge difference. Okay, so you can shoot all the way to 0.9 neighborhood because the eta is bigger. Typically, we actually have some parameter choose beta. It's like one neighborhood is the beta, another neighborhood is 2 beta. Beta is something strictly between 0.5. They still keep you in the interior. That will do tremendous help to improve the, okay? Because in the second part, I'm going to talk about the coverage of the central path. The worst case, square root n. In the good case, maybe log n. Even better case, even constant. So virtually right now, interior pointer algorithm solve these problems. Empirically, the number of steps is not square root n. It's more like a log n. Maybe that's what the most linear program is, the coverage. I'm going to talk about, actually it's all this path following algorithms all depend on how smooth of the central path it is. Yes.
Is there a canonical example that makes it a square root n, just like clean cubes for simpler?
Yes, that's an excellent point. Actually, you can prove the cleanability of those kind of things. They do need a square root. Okay. And more precisely, with this adaptive algorithms, right now we have one-step analysis. We know maybe not square root n, it's n 1/3.
Is the instance hard to describe?
It's not hard. It's not hard to describe. It was just say if you follow this central path following algorithm, we can construct the LP from one point, decrease this by a new point. You need the convergence rate cannot be 1/n cubic root. Without the Newton step can only reduce, can come back. So this is a lower bound. So I don't know. I recently saw an archival paper. They use different representation of central path algorithms. They're still like central path, but represented by some square root. I don't know. Aaron, you see the paper? He proved he have a complexity square root n become log n. I saw that that's impossible now, right? Because we have at least a cubic root. I don't know. Yeah, it's somebody from MIT claimed.
How is it?
Yeah, very recently, a couple of weeks ago. So he sent a paper to me.
Is there some class of linear program, say, where we know already that it can be root n? Like at least some special class of
Yes. There was some kind of a class. Later on, I'm going to talk about the condition number for different LP. Those condition number dictate how hard it is. It's also related to the recent work. Basically, analyze what's the coverage of the central path. It's all characterized by central path. The coverage. I'm going to define what's the coverage. You can imagine, if you have a path relatively smooth, you can still within this neighborhood, you can travel very far without the escape, without the jump from the neighborhood. Use this piece 1 second. But however, if the curve is really curved, you cannot speed too much. It's all linear programming is governed. All these interior point algorithms path following is how smooth, how you see. So you can think about this. You can think about this path following algorithms. What do you do? You can think of this adaptive algorithm. What they do is they just doesn't matter. It's all use piecewise linear, right? So give you a curve, algebraic curve. How many segments of piecewise segment you can move from one point to another point. This is I'm going to talk about. People developed this called the sequential piecewise line segment complexity. It proves the iteration of interior point is associated with how much line piecewise line curve can approximate arbitrary algebraic curve. Yes.
So just to follow up on Thatchwell's
Yeah.
question, I can't comment on the login thing.
Yes.
Or I don't know about that. But just to clarify, so the condition number measures, are there ones that govern like whether it's like root n or n to the 1/3 as opposed to governing how many beyond root n you need to get an exact answer?
I think it's beyond the root n.
Yeah, so is there any, I guess, my interpretation of your question is there any condition number that tells you when you can beat root n? For even just like having the error as opposed to solving it exactly?
It's really depends on how many layers. So if you take a look at linear programming programs, so there was an unconditional number which governs the square root n is the largest one minimized at any given mu central pass point. We have x mu, right? What is the largest one? It would be nice. You know, when you have x mu, when you have this x mu, sum goes to 0. Sum goes to analytical, to some number, which is analytical sample, sum g. If the range of this value all stay together, this range, this like a dual side, they all also have same magnitude, goes to 0. Okay, it's together. That's the govern. That ratio actually, you can prove actually you don't need square root n.
Okay, thank you.
Yeah, this is one way to do this. This is one way to define. So the hardest part, including claiming even for simplex method of actually for when simplex method applied to the MDP problem. Again, this number is it's like you don't want to have some one variable is exponentially larger another one, but which still positive. Next exponentially larger one which still supposed to be positive at the whole solution. So you have this kind of crazy layers of things, create different things. So anyway, so this is I'm just yeah. Of course, there was another way what the people also developed because in the original Kamakasa algorithm is called the potential function. Why don't we directly minimize those volumes, you know, and then we create some ratio, which is the volume of polysolve. This is the product of a linear objective combined together. Can we have algorithm directly minimize those things? People want one. Without one criticize past following is because they don't have, it's very hard to manage adaptivities, okay? But however, if you have a single function and minimize, each reduction and minimize more, the better of the algorithms. So that's what, you know, then you can introduce a step size, a parameter, and all those kind of things. You don't have to follow very sophisticated rules on how to design your algorithm. You just minimize the single functions. You know, that's what happens in AI training. You just construct a single question, minimize it. Okay, I don't care how you minimize it. You just minimize more. So anyway, I just wanted to see the question is you can still solve the same system equation, but here you can adapt the size. This step size does not governed by the neighborhood. You can go beyond the neighborhood as long as the level size is still decreasing. So this potentially gives you an even larger size. So I'm running out of time, so I just move very fast. Okay, so it's just to get this so-called potential functions. You can minimize. This is a rho. Rho is the n plus square root of n. Another nice thing about this, once you have a single question, you can also do alternating. So this is so-called potential function. So this is a primal variable. This is the dual variables. You have a joint logarithmic. So it's like a volume, different. You can represent this by duality gap. It will become a linear function. So one method is fix the y as you minimize this x. That's what's the original Kamakasa potential function. Here, assume you already know what's the optimal value. But you can use alternating strategy. So you minimize fixed y, fixed value, only minimize x until you cannot reduce anymore. Then you can prove now it's 10 for y to make a movement, for do to make a movement. So it's like a primal, go, as far as you can go. If you cannot go, you can prove, then is the deuce 10, you can make a substantial improvement. Okay, so this is an alternating method, very popular in machine learning community, because they don't want to move everything together. They want to divide them, conquer, and move this fast and fix this. Okay, so this strategy, which is also implementable. So this is actually forced to prove the same complexity. And also this alternating strategy was also forced to extend to solve SDP. But I don't know how many people heard about SDP, which is also very point. So far, the most popular method is interior point. For LP, you cannot say interior point method dominate. Simplex still very, very popular. Yeah, you can. Then another way is you can do. Since I have a single function to minimize subject to linear constraints, you don't have to use Newton method. You can use a first order method. That's also nowadays very popular. Okay. I don't know how to develop a first order method for path following, because path following is very algebraic. You have to satisfy those system equations. You have to solve system. Linearize it, it becomes solve system equation. But if you have a single function, minimize it, the more you minimize, the more converges faster of your algorithm. And if you say, oh, Newton method is too expensive, I can use a first order method. Okay, so I just give you an idea. A very popular approach for the people develop a real LP solver. Okay, they actually use the first order method as a start with. Still give you a better central path or good initial point. Then the shift to second order method. Okay, so the speed up typically for depending on what's the accuracy. For high accuracy, first order method basically broke down because they have this 1 over epsilon or something dependency. But the second order is immune from high epsilon, but still fast. But if you use this first method, give you few steps, give them a very good initial point of a second order to start with. You basically get rid of those bad central path point, and then usually your convergence very fast. So that's another advantage. Okay. Yeah, I also just wanted to know, I don't know how many people heard about the heard about the linear complementarity problems. Linear complementarity is defined by any matrix, a square matrix, M, S equals mx plus q, x greater than 0, s greater than 0, and then the complementary. So this occurred in many equilibrium problems. I just wanted to know this potential reduction algorithm. Of course, if this is M is a skew-symmetric, that's the LP. If the M is symmetric and monotone, what's the monotone? Means this, for any difference, M is greater than 0. Basically, M plus M transpose is symmetric positive semi-definite. Then this basically become a convex QP. Okay, so this is all, so this is what extend to this. But however, there was some other matrix which happened in some equilibrium analysis. You can use this which depend on so-called condition number. For example, you can generate a point over here, depending on some kind of a condition. It's called lambda. Lambda is the least eigenvalue of this guy, could be negative. Okay. However, it's also depending on what's so-called this gamma, which is called the matrix condition number for P matrix. Anyway, this problem is not convex, but you can still be able to solve it. depending on condition number. Okay. Also, you can get rid of some epsilon stuff. Okay. So anyway, so initialization, you can give many people worry about the initialization. You can construct a prime module or whatever to do it. Okay. So yes. So this is you can develop. So you don't need to worry about whether the initial phase origins have an interior or not. Okay. For linear programming, everything. So that's the current, for linear programming. But what's the final? Are we near to resolve that big question, whether LP have a strongly polynomial or not? What do you mean strongly polynomial? Convergence is exact convergence. The number of steps or number of iterations or number of operation, arithmetical operation, only depend on dimension or polynomial in dimension. Okay, so I'm going to give maybe, we'll take some break, and that part only need half hour to finish. Because it's more open questions than answers. So give it to you guys. Shall we take a break? Okay. Yeah.
Thank you. Any questions before the break?
Each version is implemented in Groby. The barrier method.
Yeah.
Each of the
Yeah. So the question is related to current commercial solver for linear programming, which method they use.
in the interior point method, which one is implemented?
Oh, so one implement is pretty much predict correct, follow that adaptively, but more practically use the Sangjin and Rocha's paper. Then they also have a lot of tune up, how to scale the things. Okay, they also have a precondition on those kind of things because the interior point eventually depend on some conditional A matrix. As I said, if you can scale the matrix, everybody, those positive variable all goes together, stay very close. A lot of tricky things. So I would say that right now, the interior point commercial solver is not the theoretical algorithm we present over here, which is add a lot of tricks to do those. But all those preconditions or those tricks come from some kind of a theoretical indications. I think that's the difference from the AI training. I don't know, those engineers they just ad hoc and just train something. Just experimental science. But yes, you need a lot of tricks, okay? How to solve system equations, all these kinds. In terms of interior polynomial and simplex method, right now, no dominance. Some problems simplex fast sometimes, but for size getting bigger, interior polynomial do get faster. Okay. Now, because the simplex method is really needed to solve integer linear programming model, they really want to compute the Kohler solutions. Okay, but even now, people, if you to start with, they start with the interior point because it's too big. Yes.
Okay, so thanks for your talk. I just want to ask an obvious question that probably everyone wants to know the answer to. So as you said, like in practice, interior point methods work extremely well. So on the other hand, we have these very pathologic instances like the Klee-Minty cube, where provably it requires a large number of iterations. I'm curious, what's your intuition about this thing? Is it maybe that for all reasonable instances, all reasonable linear programming instances that we can represent using, where we can write the numbers using, logarithmically many bits, maybe the central path is short enough, it's not so curvy that actually we can prove something, that interior point methods actually provably must converge faster than root n iterations?
Yes, I think Aaron probably also can answer that.
But what are we missing? Because like in sparse instances, we still don't know how to prove anything like that in the general case.
Yeah, So I think it's very hard to identify which one is the easy LP, which one is hard LP at the very beginning. But one representation is the size of data, it's like an L, right? Another is some condition number, but some of those condition number, even compute them is very, so it's very hard to
I think that is a great question to lead into some discussions over the break. I guess we're a bit over time, so let's thank you again.
So actually, the second part is answer some of your questions.
So
Is there a smoothed analysis type?
yeah, we're going to take a break. Thank you very much.
Okay.
So thank you very much, Yinyu. So based on the timing that you said, if this sounds good to you, let's take a break now until 3:45. I want to make sure everyone properly has their coffee on this Friday. And then we'll come back then. That'll leave 45 minutes for the final session. Does that sound good to you? All right, let's do that. So see you all then. Thank you. Yeah, that's not a short question.